Hello everyone. What we're trying to do in this video is we're trying to show that the Arcsine probability density function is a valid distribution function. So if you recall the two conditions for a continuous probability distribution in order to be a valid distribution, one is that the function has to be positive. Now we can assess that by the following. All the components of this function pi x and 1 minus x under the radical sign over the domain from 0 to 1. We know that pi is of course positive, right? 3.14 and change. So that's kind of a given. Next, if we look at x and 1 minus x, both of those factors are also positive over the domain from 0 to 1. Right? So in the denominator we have product of all positive factors, therefore we can imply that f is positive. Okay, so that's the easy part. Now let's show that the area under the curve over the domain is 1. So that's what we want to do next. If we can do that, then we have established the validity of the distribution. So we want to show that the area is 1. Again, over the domain from 0 to 1. So the integral I is going to be 1 over pi, and 1 over pi is usually what we call the normalizing factor, is what essentially will help us. It will multiply by most likely a pi to give us the one that's intended here. So the limits of integration is going to go from 0 to 1, and then dx square root of x times 1 minus x. Okay, now at this point what we can do is actually we can make a substitution. If I let u be 2x minus 1, then du will be 2 dx, and therefore 1/2 du would be dx. Now let me also mention the reason that I'm making this substitution is because it is possible to show the integrand, and in fact I will include a link to this integral that I have done separately for my calculus class. I will show that this integrand will become what I'm about to show you. It's going to be 2 times integral from 0 to 1 of dx over square root of 1 minus 2x minus 1 quantity squared. Again, I'm skipping the details so the video won't be too long, but I will put a link to the video that I have shown this. Okay, so it would make sense now therefore to make that u substitution that I proposed. Now once we have that, then we can rewrite the integral as 1 over pi times 2. The limits of integration will change. They go from -1 to 1, and of course half du, there's 1/2 of, here's du, and I have square root of 1 minus u squared. Okay, and clearly we know the limits of integration going to go from -1 to 1 because when x is 0, u would be -1, and when x is 1, u is going to be 1, right? That comes from this relationship. So that's established, which forms the new limits of integration for us. And of course the halves and the half and the 2 in the front will cross out, and we get an integrand whose integral actually is known to be arcsine. So we recognize the integrand as the antiderivative of arcsine, evaluated from -1 to 1, and that's going to make this 1 over pi the arcsine or inverse sine of upper limit minus the lower limit. We did the fundamental theorem of calculus there. Now the arcsine of 1, remember the output of every inverse trig function is the measure of an angle. So if arcsine, we want to know what arcsine of 1 is, so the measure of angle is arcsine of 1, therefore by definition of the inverse, sine of theta is going to be 1. Now we know that sine of theta is 1 within the range of the inverse from negative pi over 2 to pi over 2. So pi over 2 is going to be the value that we're going to use. And then for the lower limit of integration, might as well do that one, where we have to say, just use theta. Let me go, I don't know, phi is going to be arcsine of negative 1. So that means sine of phi is equal to negative 1. And again, therefore, phi is negative pi over 2. Now, the reason we don't choose phi to be, for example, 3 pi over 2 is because, remember, the range of arcsine is between negative pi over 2 and pi over 2. It's for that reason. Okay, let's plug these in. I'm going to have 1 over pi arcsine of 1. We just show that that's pi over 2 minus and negative pi over 2. And those 2 pi halves makes a whole pi. Therefore, there is your normalizing factor, and the integral evaluates to a 1, which is what we wanted to show. Therefore, we know that this is a valid probability distribution function at this point. Now, let me just make a note here for the integral that we just did. The integral of dx over square root of x times 1 minus x turns out to be the arcsine, but that's, we just showed that, 2x minus 1 plus a constant. So bear that in mind. Okay, so then why is the distribution, by the way, is called arcsine? Well, because there's definitely nothing here that suggests the arcsine, right? So the reason for that is because if you look at the cumulative distribution function, and in fact, let me do that for you real quick. If you look at the cumulative distribution function for the arcsine, so that would be the CDF, cumulative distribution function. That means, by definition, that's f of x, and that is cumulated over the domain from lower limit up to some arbitrary x value within the domain. So here x lies between 0 and 1 of the PDF, the density function, t1 minus t. Okay, and then I can write this as 1 over pi. Now, the integral of this, the integrand, once you evaluate it, the integral is going to be arcsine of 2t minus 1 evaluated from 0 to x. Okay, and now again we're going to place the upper limit and then subtract the lower limit. And when we plug in the x for t, we get 2x minus 1 minus the arcsine of, we plug in 0, we get negative 1. Okay, and we just showed again earlier that the arcsine of negative 1 was pi over 2, correct? So this is going to be arcsine of 2x minus 1. Negative of a negative pi over 2 makes positive pi over 2. And then there we have it. We can now distribute the 1 over pi, and the cumulative distribution function is going to be 1 over pi arcsine, and hence the name, arcsine of 2x minus 1 plus 1/2. And there you have it, the cumulative distribution function. And again, here x must be between 0 and 1. Okay, and don't worry about the endpoints here, whether why do we not include equal sign? Remember, in the beginning, the endpoints were not included. But then in the case of a continuous probability distribution, remember, the probability at a point is 0. So probability of x0 is 0. Probability of any exact value is 0. So that's not going to break this for us. And the other expression that you may also see for this is, let me do that. I'm going to make this note here. Remember the integral of dx over square root of x 1 minus x. We said that was arcsine, right? Well, I also have shown that in my video, that I will have a link for you down below for it, that this is equal to -2 arc cosine of u plus a constant. So if we go with this version, then of the integrand, or the integral, I should say, then the cumulative distribution function is going to be 1 over pi times -2 arc cosine of square root of x. And here u is square root of x. Again, in my video that I have a link for you in under the comments, I've shown this to be true from 0 to x, and this is going to give me -2 over pi, factor the -2 out, and then I have arc cosine of root x. And actually, hold on, I'm going too fast here. Let me tidy up this expression so it looks right. This is the u1 minus u. Okay, and in terms of x, so this would be u. All right, now it looks better. So the arc cosine of square root of x minus the arc cosine of 0, and inverse cosine of 0 within the range of cosine inverse, which is from 0 to pi, is going to be 0. So this is simply going to be -2 over pi times cosine inverse root x minus 0, which I just won't put there. There you go. That's just 0. Okay, or actually, hold on, that's not 0. Let me see. If theta is arc cosine of 0, oh, so it's going to be, yeah, okay, actually, let me see. That's not 0, I'm thinking sine inverse. So that means cosine theta is 0. Oh, okay, so theta is going to be pi over 2. Okay, let's take this off. And again, because the range of inverse cosine lies between 0 and pi. So this is going to be -pi over 2. And now I can multiply the coefficient. -2 over pi times -pi over 2, that's just 1, right? -2 over pi arc cosine of square root of x. And again, this is what you may see as another expression for the CDF. So we have two expressions, one in terms of square root of x, the other one is in terms of 2x minus 1. Both of these are valid. Okay, and that's all we wanted to do in this video. I hope that you find this useful, and with that we are done.